to, I guess, to moderate, although really Patrick's doing all the work. So yeah. So, anyways, just to get started again, the Project A are these mature technologies that have been either cranking away for a little while now and are at a point where they're about ready to go into something more like a pilot scale, or do more field scale testing, and a few technologies that are really modifications of existing operation that are probably also ready. And so what we're looking at in the continuum is implementation, piloting, and demonstration for these, whereas the others are a little more still mired in the early stage laboratory development. And so we've got a number of, a total of 7 projects that we'll touch upon, but we'll spend most of the time on the first 3, 1, 2, and 3, because, and a little bit of 4. They're all 25-minute, I think. Yeah.
3 25s and a 10.
Just to refresh your memory, this group that I showed you just a minute ago, and so we'll, as I say, we'll focus mostly on the ferrate, the coagulation, and the ion exchange. A little bit on natural filtration, and these will be just a little bit of a taste of what's to come. And this is the mapping for all of these too. Going back to that the table that I showed you just a few minutes ago with the health effects violations, or the health-related violations. And so we've got some of them in almost each one of these categories from Group A. Anyways, as a result, you've seen a little of this, but what we'll do is we'll just jump right into the first one, which is ferrate, and John's going to talk about ferrate for 25 minutes or so. So we'll go to the next slide, and that's so you're on that.
Yeah. Hi, everybody. Chance to talk about ferrate, although Dave could or should do this as much as me. This is just a mention of our group. So this is a project that began with an EPA project number that's here. So one of the 3 projects that we incorporated into the Wind Center that were prior EPA projects. So this is a group of us at UMass that I stole this slide from Dave. He was down under recently advertising our group. So Joe Goodwill just finished his PhD last August. And June's finishing this summer. Josh is he's a master's student. He was a bachelor's student at Haskell Indian Nation in Kansas, and worked with us as a summer intern, and then came as a graduate student at UMass. And Schwinn was an undergrad when she worked on this, but now is a master's PhD student with me at UMass, staying at UMass. So just tell you that team. So the idea here is we're focusing on ferrate as a treatment technology, and as I mentioned, it's built on the STAR project, which really just ended in November. And so most of last year, in terms of money and time, and most of the output that we've put out, at least in the written literature, is from that study formally. We haven't spent a lot of the ferrate money within WINS yet, because we had this other work ongoing. And the idea is to move into continuous flow experiments, more so than batch lab scale. And I'm going to talk about some of the general things about ferrate to bring people up to speed, and then what we're working on now. And in terms of target utilities, I think Bruce did a great job in telling us all to fit each project into a certain paradigm. This was one of those. In terms of target utilities, it depends on the contaminant in this case. And Orrin earlier mentioned groundwater versus surface water. That's one thing, but it's particularly the contaminant and what role that ferrate might play. So if you look at a typical surface water slide, and this little box I put on here, almost all these slides I've stolen from my students or Dave or something. So I should have put a box on all of them, but I didn't. But most of them are from Joe, so we'll just leave it this way. From a job interview, and he got the job, so I figured they're good, right? But ferrate, if we look at a typical surface water treatment train, maybe could have a role here as a pre-oxidant, so I'll mention that. And if I use the word intermediate oxidant, it means after some clarification particle removal and then prior to a particle removal filtration step. We're going to talk about its role as an oxidant, its role as a disinfectant potentially, and that's in brackets here. And for that reason, it's been touted over time as a great green chemical. So we'll look at it. What is it? So it makes a nice purpley pink solution. So if you know permanganate very well, think a lot of parallels with ferrate, both in terms of what it looks like. We use a potassium ferrate salt that we make a solution of in med. So think of it, the hope is to go that would be its place. You'd get a bag of potassium ferrate instead of a bag of potassium permanganate, perchance, maybe. It decays. That's what we have to look at. It's often been touted as a role in coagulation. We've actually got some real data on that, and there hasn't been much. I think it's less promising there than maybe always written about, but it has a role. A big thing is that it doesn't make halogenated disinfection byproducts. People used to say it didn't make any bromate. One of our students is just now finishing a paper that it does make some bromate, but it's a really complicated group of oxidants and things that happen. But overall, ferrate, iron 6, decays to make iron 3, so it gets reduced. It makes some particles, just like permanganate makes manganese particles, and so it has some serious parallels there. This is from Dave or Joe. Or ferrate chemistry is that, like permanganate's anion, when we dissolve it in water, it has a bunch of pK. So in the range that we're usually working in, the predominant species are the monoprotonated and the unprotonated species in the range that we're usually working in. Makes it ferrate's oxidative capacity and its rate of decay is very sensitive to pH. So it decays much faster as pH we're in here versus here. So it's this chemistry is important in its role as an oxidant and as a participant in processes. So Joe put this together. This is just a snapshot of, there's lots and lots of ferrate papers on its role in the laboratory, in a beaker, doing something. So examples of that are, this is triclosan degradation over time in some seconds. This is killing MS2 phage over here. These are various reduced species getting oxidized in organics and organics. So it's long been touted, I mean, for decades, as a strong oxidant.
Sharma publishes one every 2 weeks.
Yeah, Sharma's rate of publication, Sharma's, I mean, there are literally hundreds and hundreds of papers. Most of them, though, are done in a laboratory setting in a phosphate buffer that does not mimic anything that happens in real waters, and it's very different that happens. So the notion is, behind this, why we've spent time on this, is that there's this green chemistry notion that ferrate can be an oxidant, a disinfectant, create some, maybe aid in coagulation, and play all these roles. So if you're thinking from why, on the one hand, it's this powerful oxidant and a little bit complicated chemistry, why would it be applicable to small systems? The notion is that it could play multiple roles if you could buy that chemical and achieve a bunch of things with one dosing. That's the idea behind it. Behind this chemistry. So there's a lot of things that, as an oxidant, it could do a lot of things. Reduce metals, changing arsenic. Neat thing with arsenic is that we oxidize the arsenic, and the reduced iron is we know iron particles are great absorbents for arsenic, so you get a double thing going on there. We could oxidize various things. We're going to say a few words about a couple of these topics that we've worked on at UMass. So one of the things is that ferrate goes from that purple thing to a suspension of particles. This is in laboratory DI water. It makes iron 3 particles, and very little work had been done at looking at those particles. So Joe, one of the papers in his dissertation was in ES&T last year that focused on characterizing those particles. What are they? And I think the notion up until there's been maybe one paper about this, was that they'd be very similar, the same as if you take ferric chloride and add it to water, and the ferric iron hydrolyzes and make ferric hydroxide. And they're not. they're different. And I'm not going to get into that paper or anything. I just can say that we've gone through that aspect. So one of the things is ferrate decay. Ferrate decays is important in the time. So look at the time scale here of minutes. This is in this case, you have the pH 7.5. If I did 6.2, they would be down in here really fast. What we've discovered early on is that all the work that had been done in phosphate buffers hides the fact that the iron would get reduced and precipitate in natural waters, and it affects the decay. So that's always been hidden in the phosphate studies done in the laboratory, because we don't generally add 10 to the minus 2 molar phosphate to most of our drinking water. We just don't do that, right? So it turns out, much to our surprise, that in natural waters, actually ferrate decayed slower than in the lab water. We walked into this absolutely certain it would be the other way. I mean, hands that Dave and I, when we first saw the data, it was like, nah, wrong. Go do it again, do it again. We did it again, we've done all that. And it depends on the nature of the particles. Are the particles fresh? Are the particles aged? All those things make a difference. So unfortunately, it's a bit complicated. There are various reasons that it would be nice if it was simpler, such as disinfection. And we'll say a little bit more about that. So I just want to mention that. So the solids play a big role, and the solids play a big role in this. So we make particles here. They're different. This is reduced. Are they the same or different? It turns out they're different. I can't go into, I think I have one picture from Joe. So these are some ferric hydroxide resultant particles. This is some ferrate resultant particles. That's what we call them. And it turns out these have different, we've done XPS and other kinds of analyses. They have a different, these are more like a Fe2O3 kind of structure versus a ferric hydroxide structure over here. They look different. They tend to make more nanomaterials, more smaller materials that get stabilized by natural organic matter. As a result, then there's a lot of surface area. So maybe it's better. Maybe they'll be as a surface to do work. Maybe that's good. But it has implications for particle separation down the line. So we've done that work. So this is a slide from Dave that he just presented in Australia. Does it decay? Is the mechanism the same? Can we count on these rates? Can we model them? Can we predict them? And we've made some progress in that, and I'm not going to share details of that, but we need site-specific studies in waters to understand this decay and how it will occur in different waters, and we need to do the pilot testing. One slide from a paper we're trying to get published, but manganese doesn't get any respect. Turns out there is no data on the stoichiometry of ferrate oxidizing manganese, but it seems uninteresting to a couple of journals in our field. I think we have a great paper that we just can't get out there. It turns out that we have got the stoichiometry of ferrate decaying, oxidizing manganese 2 to manganese 4. And it does involve in this using 3 electrons from the ferrate, so Fe6 to Fe3. There's a lot of reactions that are 1 electron transfer reactions. Some are 2 electron transfer reactions with ferrate, because you start at 6 and you can go to 3. So what's happening? And it turns out with this one, it looks to be a 3 electron transfer process. So we've got a bunch of papers that I have that submitted. I'm hoping the current place will make it work. So a couple of moles of ferrate per 3 moles of manganese. So that's get your electron balance there. Joe has analyzed the solids that are formed on this particular case. It's really fast. Really, it's a very, very fast oxidation. This is one particular setting, pH. This one is 9.2, so really high. All right. So what happens? The reason that we don't have it for pH 6 or 5, we can't measure fast enough. In other words, the fastest point of measure, it's down here somewhere, is where it happens at pH 6 or 7. So it's really, really, really fast. So in the best attempts at within reason chemistry we can do in the, Joe couldn't get a number fast enough, but he got one at 9.2.
What is the measurement of ferrate? What are you using for indicator?
Yeah, I don't have time to talk too much about methods, but in this particular case, this is probably direct photometric. So when you want to do something at this scale, you want to do absorbance on a spectrophotometer. One of the problems with that is the ferrate resultant particles cause scattering of the light, so it gives you a problem. You never get to 0. This has been subtracted probably. There's a baseline, and that's a little dicey. The other method is the ABTS method, which ferrate oxidizes a molecule that absorbs very strong. It's very green. It makes a great green color in the lab. All right. So, Yanjun did a whole lot of work with batches of water and adding ferrate. Then we looked at a whole bunch of studies on the impact of DBP precursors. So right now I've mentioned particles, decay, manganese, and then DBP precursors have been a focus. Not shockingly coming out of Dr. Rickow's group, somehow. We looked at this, and this is a graphic on a paper that's just got accepted at Water Research as the graphical abstract, and I'll just use it here and throw a few words. So the idea is that if we add ferrate as a pre-oxidant, we assessed its direct oxidation capability. It's not dissimilar from ozone, for example, in that. Then we looked after coagulation, with and without this, was it markedly better than just doing coagulation? And just like ozone and other oxidants, a lot of the precursors that you remove in coagulation also react with the pre-oxidant. So if you take them out from coagulation, the net benefit after coagulation is less than what the apparent benefit here. And then it turns out, so we do get better impact going this way. But then if you use a ferrate as an intermediate oxidant, which when we started the project we weren't going to do that at all, it turns out to have a much more substantial impact. The challenge with it compared to ozone is that if you use it as intermediate oxidant, you make particles. So now we have to remove them here. And we've done that, of course, like in the lab, it's easy to do that with a syringe filter. But in a continuous flow experiment, actually that's the next step of what we're doing. So these are some whole bunch of natural waters we did in the prior project, and their impact. This is raw water impact. And we have mimicked in the lab what we're going to do pilot work, and you saw it, actually Dave showed it on the mobile pilot. These are upflow roughing filters. They, unfortunately, when this first came out, it was branded an absorption clarifier. It's the stupidest word, there's an absorption going on. It's a roughing filter, right? These are several millimeter sized plastic beads. The water goes up here at about 10 GPM per square foot, goes over here and goes down through a media filter. Do a media filter at 5 GPM per square foot, roughly, design thing. Great process, used extensively in New England. And from a piloting perspective, I'm looking at Jess here a little bit, anybody who's done a lot of piloting, it's really hard to pilot gravity separation processes at anything of a smallish scale, right? Gravity process, flotation or settling don't scale down real well. So what could we do at the pilot scale to mimic clarification? And this process is probably the best shot at that. You can do that at a small scale. So this happens to be, West Tech happens to be where this sits now. It's under many other names over its life. So our pilot system in the lab, it was great, out in your parking lot. Did you see it, Patrick? Dave?
No.
Oh, wow, right out here. So
I
we have Big Bertha.
They have a Bertha.
We have this is Big Bertha, but we don't have that trailer out in the parking lot. Yeah, so it's on a little rack here, and some of our students have spent harrowing times transporting this in less than OSHA type vehicles, right? 300 gallons of water.
As it turns out, she's very heavy.
She's very heavy, she is. Anyway, Bertha's here. This is a pilot scale system, and there's pumps, chemical feed, upflow roughing filter, downflow filtration, and I'm going to show you another picture. Just behind it now, on the other side of the rack, is intermediate ferrate, actually a place where we can do intermediate ferrate. Notice the scale, the flow, 0.5 liters per minute. This is a very small continuous flow experiment. It took me a while. Our students wanted to call this pilot work and the bench scale stuff, or the other stuff, bench scale stuff, and I said, no, you gotta go, it's either batch or continuous, and they're all lab scale. They're all really small scale, but there's batch experiments and continuous flow experiments. That's the difference. So this is some ferrate feed solution, this is some ferric chloride, and there's some pH control, so you have all those things. So it's a bunch of controllers. Joe did a great job of connecting them all up to a computer. This is the upflow clarifier. Just behind here is now a ferrate, it's on the other side, you can't quite, it's over here. There's a ferrate intermediate contactor, and those experiments starting last week. So the upflow roughing filter captures a lot of iron particles in this case, and removes them. And you get some outputs that, this is just one particular output. We were primarily wanted to see we didn't have cause problems with performance. And in fact, the pre-ferrate was better than without ferrate in terms of turbidity, some particle counts. The head loss slide, this is inches of water. Basically, the clarifier, this is a problem with upflow clarification. It basically does such a good job that you don't have much loading to do a media filter, so you can't have much impact, right? So we're going to look at a direct filtration mode as well, which we haven't done yet. So this is from Dave's slide. So this is pre-ferrate. We looked at we saw a similar slide before, pre-oxidation import. This is the impact relative THMs. This is 1 here down to 40%. This is intermediate ferrate. We dose at 20 micromolar. We can do another 30-40% decrease in DBP formation potential by doing intermediate ferrate. So that's why it's interesting to look at. Does it make biodegradable organic matter like ozone might in intermediate setting? I don't know. Maybe. We don't know.
Are those groundwaters?
No, these are all surface waters.
Okay.
Yeah, these are all surface waters so far. Yep. They're all surface water plants, and in fact, at least 2 of them, there are plants that use the full-scale technology, the exact same as the lab-scale technology that we're using. Upflow absorption. Excuse me, I said the upflow roughing filter. In terms of our next steps and challenges, we've got the lab-scale intermediate ferrate experiment just starting. Bertha was filled with some water that sat around for months, and we're just kind of using it to make all the, no leaks and chemical feed and whatever. And now we're going to go out and get a water to do actual testing on for intermediate ferrate work. Looking at DBP FP, I haven't talked about disinfection very much, so I'll mention that down here. We've got to do a lab scale pilot of groundwater. Now, there's some challenges. Lab scale piloting of groundwater is challenging in the following case. My experience is it is not possible to bring a groundwater that has any reduced iron in it into the lab and do anything that's like reality. So you have to stop right there. It's just a waste of time. I've tried. I mean, I've put nitrogen in bottles and carried it, and it's just, reduced iron is so susceptible to oxidation that you don't have the same water that's in a sealed pipe under pressure from the groundwater pump. You have to go to that space and do it. I've done it with sequestration studies a lot. You have to go there. So if we're going to do this, we need to go, fortunately, next door to Amherst in Hadley, Massachusetts. There's a groundwater that doesn't have any iron. It only has manganese, and they're currently doing permanganate. So we might grab some of that water and we could do a manganese. We have done a little bit of bench scale testing on arsenic. There are some groundwaters, small systems that have that issue in New England and Massachusetts that we could bring if they don't have reduced iron, and do that. And we'd like to get this into the pilot plant. What are our challenges? I haven't talked about this, and this is the elephant in the room, so to speak, is that you can't go buy ferrate right now, right? It's not possible to go buy potassium ferrate at the moment. There's a process that's licensed and patented by Battelle that was licensed to a company that made ferrate. And when we started this project, we bought it from Sigma Aldrich and got going. And then the next time we went to buy it, it was back ordered, and it was back ordered, and it was back ordered. And we got into it. We got some from friends at various places in the country that got some to our lab. That has to be overcome. We have an agreement with Battelle that we're trying to work with them, and I think Dave's trying to promote the notion that it can be commercially produced. It's a bit of a chicken and egg. They don't want to go into production if there's no demand, but we can't test it full scale if we don't get kilograms of it. Grams don't count in the piloting world. You need kilograms of it. So we're in a bit of a catch-22 right now. There is a process that is called ferrate. One example is Ferrate Treatment Technologies, FTT, but it makes a product that really is antithetical to drinking water treatment. The pH is really high, the sodium is out of sight, and at least when we actually, they came to UMass, our students learned to make it in the lab, one non-disclosure agreement, we made it in the lab, but we kept finding this exorbitant oxidant demand. And Jun's doing this, the ABTS method, and the moles don't add up, man. It can't be that much oxygen. Well, turns out you make it with chlorine, free chlorine and ferric chloride and sodium hydroxide. And the product had excess free chlorine. We're using ferrate because we don't want to use chlorine. So we cannot have a product that has excess free chlorine in it. It's not possible. So we were a little, I don't think you were misled, maybe, I don't know. We certainly hoped, they advertised it could do it, but I don't think it's possible. So to me, I think to us, a potassium ferrate salt product has to be the thing that people get. So right now, we know how many berthas of ferrate we have in our lab. Like, a bertha is 350 gallons, so we know how many experiments we can do, but beyond that is a challenge. The other challenge is, I think, for ferrate to make it a go, is that a utility would need to be able to say, I can get CT disinfection credit with this chemical. And right now that's not possible. And Dave has been working with EPA, Mike's been involved in this as well, in trying to get those studies done, CT studies done. So you have a CT table for ferrate. There's two challenges. There's challenges doing the work, and then like all disinfectant credit in the United States, we have to be able to measure something that we then calculate a CT from and report that. And the measuring side is not trivial on the case of care, as compared to chlorine or ozone, or I mean any strong oxidant's a challenge, but this one is even more challenging.
So let's go ahead with the design of the CT studies. UMass is going to play a role in.
Yeah, the statistical design of the CT study. Because I guess what EPA actually didn't conduct the prior CT work for other organisms and other disinfectants were data gathered in and created that, but that data isn't out there.
And if you can imagine trying to develop a brand new set of CT tables on all the experiments you have to do, and right now we have to, because if you're looking for chlorine replacement, you're looking at HEP and Giardia, and no one wants to do Giardia because it's animal activity. It's a lot of work, and so if you try to fill out a full CT table with all the controls and all the replicates, so you have statistically based margins of error, safety factors, you're looking at a lot of dead mice. So yeah, a lot of money. So we're trying to come up with a clever experimental design. We can minimize the number of experiments, and also maybe target maybe a different pathogen that might be more appropriate, given this is 2016. So
yeah. So it's
We do then also have to, issue a addendum to the rules.
yeah, I mean, with any new technology. I mean, similar to what UV came in with the stage 2 and all that.
Right.
Well, I shouldn't say stage 2, but with the LT2. But yeah, we'd be looking at this again. This is part of what you guys will be dealing with in this small system. Any new technology, what do you do? I mean, right now we have groups that are working with UV trying to get state acceptance. Even that is developed as that is. It's not slam dunk. So this would be a lot of rule making and stuff like that. But we're trying to get ahead and start working on the disinfection now. But be smart about it.
Mm-hmm. Yeah, that's one of our people at UMass and a student who's going to be a professor at Cornell is really good in statistical analysis and statistical design. Scott Steinsoner, yeah, the water resources guy, but he's good in statistics. All right, so I think in terms of outputs and outreach, almost all of these were, so it's been fun. We just had a phenomenal team, Dave and me and these two students. We've just done a lot of work, particularly Joe and
Two students.
What? What?
The two students.
They are phenomenal. Yeah. We try to stay out of their way. But these guys have been great. Put a lot of papers either out or in. The next thing that's an output. We recently in the joint newsletter, there's a little article on this ferrate project that's in the Joint Center newsletter that came out. Got some project presentations at AWWACE. I'm going to hopefully Norway and make a presentation. So it's a particle separation conference, so it's kind of about the ferrate particles, as you might imagine. Hopefully Des will be there too at this conference. And then the next thing I anticipate is intermediate ferrate on the pilot scale is the next thing going on. I didn't say very much about the bromide stuff. Others that have spawned from our group. I could show an interesting slide. A former postdoc of the center, Karu Ikuma and Joe have submitted an NSF proposal that was about disinfection and had some preliminary results. So I think these two roadblocks about making ferrate and at CT are critical to overcome because it's got so much potential. When you have this chemical that does the byproduct problems, has all these strong oxidant and disinfectant capabilities, it would really be nice to harness it. But there's roadblocks there. And at least we've overcome, I think, There was just not a lot published in the real world of drinking water. Lots in the laboratory beaker, but not much in the real world of drinking water. And I think we've.
Still, if you can show that it's a really effective oxidant and doesn't create any other weird issues
Yeah.
in natural water, even without the CT, there's places where we might apply this that would make
Yes.
sense.
Yes. Yeah. But it would be. I mean. Yeah. Yes. Yeah.
Is it expensive? I suppose.
It's theoretically infinitely expensive right at the moment. But,
Yeah.
Priceless.
priceless. Yeah. And there are folks around the world working on this.
Yeah, it's hard to know where the price point would be in this, but it seems like it's in the range of the technologies that one would use for GBP control, for example.
Yeah.
And
Yeah.
certainly cheaper
In the
than
range
ozone.
of chlorine dioxide.
Yeah.
It's not as stable as a potassium permanganate
Yeah.
solution. So if it was it might be a half-day tank, not a day tank, right? I mean, it's something that you'd make up more, but the chemical itself could be stable in a beaker.
That's probably.
But it decays
So-
more
so
rapidly.
quickly that you have to use it like that? So that
not
you're
like
mixing
that.
batches every 6 hours or something?
No, the Sharma.
Hopefully not that quick.
Sharma is.
Takes it out of the lead.
No, it's actually maybe longer than that.
Yeah,
because,
yeah.
Brenda Sharma has told us that he has found a way of stabilizing the ferrate for a day tank. And so that it truly would be, I think, a day tank, 24 hour. And I think he's possibly planning on a patent that. Because he hasn't told us exactly what he's done. But he's probably added something to stabilize the decomposition and who knows what else.
A lot of the laboratory researchers that make it themselves, do organic chemistry.
Right.